Give me a moment. Okay. Okay, so I want to talk about, go over like some quiz questions, and then since there's really not much he did, I believe last time in class, all he did was like prove like factorization is like unique, right? And then go over like cosets. Is that right? Okay. So I'll review cosets because I feel people forgot group theory. Is that true? Yes, no. There's actually a lot that goes into cosets. So I'll do that after I go over the quiz and like homework and stuff. So there was a homework problem that like if you remember like the give a subdomain of an integral domain whose field of fractions is the same pretty much. Um I don't know. So the grader apparently marked people off for giving the wrong. I mean, like a trivial example. So technically, the trivial example is correct. So basically, you want D prime subdomain of D. So strictly not equal. Um, where frac or does the book use frac or quotient? Whatever. Fraction field or quotient field are the same, right? So the trivial example would just be let D prime be Z, D be Q. Yeah. So this is integral domain. I don't think that's what they intended. Like when they write integral domain, they sort of mean something that's not a field, like just only an integral domain. So I think for this, if the grader marked you off, you might have to tell the professor, because I mean I don't know if the grader is gonna, if there's an easier way than like checking one by one and refixing each person. I think the better way would just be to like null this question. I mean, I can sort of see why. Like, I mean, I'm pretty sure the author did not intend for you to do this. Like, I mean, or else there's no reason to ask the question this way, right? There's no need to introduce D prime, three things, right? If the author just wanted Z and Q, then like there's like you know that's sort of like redundant to introduce D prime, right? So uh so the I think the answer they wanted was you want D prime to be Z, right? And you want like D to be something in between Z and Q. So some people got it, I think. So what I suggested was like Z of like, I mean, basically T to be the set of what did I put T? D to be the set of like, I don't know, A over 2 to the R, where AR is in Z. Yeah. So this should work. Yeah, because certainly these are this is a subset of Q, right? And you could check the fraction field is still Q, because I mean it's the smallest field that contains this. So and it certainly contains the integers, right? Because just take R to be 0 and A to be in Z, right? So 2 to the 0 is 1. So you certainly contain the integers. I mean, and you could check. I mean, it's certainly commutative, and it's a ring because a over 2 to the r times a1 over 2 to the r1 times a2 over 2 to the r2. This is just a1 a2 over 2 to the r1 r2, right? Plus r2. I mean, this top part's still in z because a1 and a2 is in z. This is certainly still in z because I mean integers are it's still so it's still something over some power of 2, right? So you can check that, I'm pretty sure that this is what the author wanted. Like the author wanted like something in between z and q. Uh, is everyone clear on this? Okay. So let's move on. So since we didn't really go over anything new, we could just go over some quiz problems first, and then I'll heavily review cosets, so everyone understands like where we're going for rings. So let me just quickly go over some quiz questions. Let z mod 7z under plus and times be ring of integers mod 7, right? So let u under multiply be group of multiplicative units. So the first question is, then u is cyclic, then u is abelian. So both are true, yeah. So the fact u is cyclic, it's from like one of the theorems in your book that when you have a field, a finite subgroup of a group of units, the group of units is cyclic. In this case, the whole field is finite, so obviously u is finite, so u is cyclic. And part two, there's so many ways to do this. The abelian part is super easy. The one thing you could use is all cyclic groups are abelian. Do I need to go over this, anyone, or is this clear? Like, is it clear that the fact that all cyclic groups are abelian? This is like exponential law. So, okay, since you're all clear, yeah, you could use that, or just use the fact that z mod 7z is a field, right? So a field is a commutative, if you like, commutative division ring, if you remember. Nobody cares what this. You mean not nobody cares, but like you don't need to know what this is. Just is this part you need to know, right? Commutative means multiplication is commutative, right? And that's what it means to be abelian under multiply. Okay. So the next question was LCM of AB is less than AB. So this is false. LCM of 2, 3 is equal to 2 times 3, for example. Yeah. So, and then the last one was just basically testing you on the proof of this, right? With the proof of this, you use like Chinese remainder theorem. And that was for co-prime things, right? Like you remember you had like Z mod DI, where D was like a power prime. So this is asking, what if they're not co-prime? Are they isomorphic? And this is like false. Yeah. Because I mean, there's so many ways to check this. One way to do is that this is cyclic. This is not cyclic. Yeah. So here, one generates the whole group, right? Nothing generates the whole group here. Everything has order 2. Everything other than the identity has order 2. So this one has order 1. All the other 3 has like order 2. I mean, to be cyclic, you have to have order 4, right? The order of the group. So, everyone clear on this? Yes? No? Okay. So, let's do one more. I think someone asked me this in office hours. Let R be ring FG in R of X. Assume leading coefficients of F and G are zero divisors. Then degree of F times G is less than degree of F plus degree of G, right? So this is false, yeah? So remember, in the case you had zero divisors, it's this, right? It's still possible to be equal, but it's less than or equal to, right? And then like over, like for example, fields, like you certainly have that this is true. Yeah, so it's certainly not the case that you could just take out equality sign. It's still possible to have zero divisors, like with equality sign. So like just take R to be Z mod 8Z. Then we are working in Z mod 8Z of X, right? So 2X plus 3, 2X plus 3. Yeah? Here, both the leading coefficients are zero divisors because 2 times 4 is 0. Yeah? But if this is like your F and this is like your G, well, the product is just 4x squared plus, well, 12x is just 4, right? So 4x plus 9 is just 1. Yeah? So this is FG. And you see that in this case, degree of FG is 2. Degree of F plus degree of G is 1 plus 1, which is 2. Yeah. So we still have equality here. Everyone clear on this? Yes, no. Okay. So let's move on to cosets because I feel people forgot about it. It's like 120A. Cosets. So there's like left and right. I'll just go over, both. Given group G star, let H be a subgroup and A, B, and G. Right, you could define like a left coset or right coset, or not like a right coset, right? This is a set of AH such that H is an H. And like certainly you could define this to be HA such that H is an H. Of course, a priori these could be different, right? Like these, because G need not be abelian, right? If G was abelian, then AH is HA. So the cosets are clearly the same, left and right. But in general, they're not. So let me ask a question. What is EH? Can anyone tell me that? Where E is the identity of G. Yeah, it's just H, right? Just go by definition. EH is a set of EHs that H is an H, but identity does nothing, right? EH is just H. Yeah, so this is just H. Okay, good. Now, Now let me tell you some nice properties, right? So let's do one, right? So if AH is EH, right? Then what can you say? So then A is an H. Yeah. So why is this the case? Well, I mean, just think about it, right? If A is an H, we are done. Yeah, because H is closed. It's a subgroup. It's closed under multiplication by itself, right? So, so hmm? Yeah, it is if and only if, but I'll get to that. You know, I mean, I'm not going to prove everything from 120, 128, but yeah, this is if and only if condition. Um, if A is not an H, then this is easy. Then it can't be possible these are equal. Then is not equal to this because H is a subgroup, right? Subgroup. So it must contain identity. Right? So if it must contain identity, what element do you know is in here? So A times E is in here. Does everyone agree? But this is just A, and if we assume A is not an H, then it can't. And we said right here that EH is just H, right? It's not possible. If they were equal, then that means A must have been an H, right? So so yeah, so we're done, right? So now, before I continue, does everyone understand what I mean by this? Like AH, like this is shorthand for when I write right AH, I mean like A star H. Yeah. Again, you have a group, right? The only if you're gonna combine two elements, don't it better be the group operation, right? So keep in mind it's star, so you're not really multiplying. It's whatever the group operation is. So for example, right? Let's do an example, right? G is the integers, H is 7z. Yeah. And let's let A be 2. I don't know why I wrote the 2 like that. So A is 2. So if it's so and then you could think of this as star too. So like 2 star H, in this case you could write it like this, right? 2 plus H. What is this? This is this is a coset, and it's the set of 2 plus H, such that H is in H, right? So it's the set of, you know, but we sort of know what H is, right? H is in 7z. Yeah. So it's the set of the numbers that when you divide by 7, it has remainder 2. Is everyone clear on this? Yes? No? So okay. So we're gonna define G mod H to be the set of cosets. Yeah. Under, again, G is a group, H is a subgroup. So it's a set of cosets, right? So a priori, how would you write the elements here? It's the set of GH, right? For G and G, right? You just take because remember, one coset, it's you take like one element A and G, right? So the set of all cosets, you just let A run through every element in G, right? Is everyone clear on this? So by set of, left or right, just pick one of it. Left slash right. Um, so this is the one thing I won't prove, but so the idea is, let me just say, cosets partitions, cosets partitioned G, because if we define um, because like A is equivalent to B in G if and only if AH is equal to BH, um, then so these are sets. Remember, AH is like the set of elements, right? A times H is that, H is an H. Same for B. Then tilde is equivalence relation. Uh, I'll let you check that for practice. Yeah. And once you have an equivalence relation, you partition your whole group, right? So what do we mean by this? By what do I mean by partition, right? So just review. Partition means like if either you have two cases, either G1H is G2H or G1H and G2H share nothing in common. Yeah, so it's not possible for them to share like two elements, right? So their intersection is either empty or the whole space. Yeah, that's what we mean by partition. So what you're going to see is it's a bit redundant to put this, yeah, to run through all of G, because from this partition we get this second property. If I take Q in GH, right? GH again. This is the set. Um, then this should be true. Yeah. So before I prove it, let's sort of see an example of what I mean. Yeah. So again, let's take G to be Z, H to be 7Z. Then again, what is G quotient H? G quotient H in this case is Z mod 7Z. Yeah. And so this is the set of cosets, right? So let's consider, let's take little g to be 1, right? Then gh, right? Then what is gh? Gh in this case, the operation is plus because g is a group under plus. So it's g plus h. So it's the set of 1 plus h, such that h is in 7z, right? So let's take Q in here. So let's take Q an element in here, right? So what's another element in here? We have like 1 plus any multiple of 7. So let's take 8, yeah? So this statement is basically saying 8 plus H is the same as 1 plus H. Yeah? And that sort of makes sense if you know what this ring is, right? Like the class of 1 is just the class of 8, right? They share the same remainder, ren dividing by 7. Yeah, so does everyone see like that this should be true? Uh, yes? No? Okay, good. So, so let's prove it formula, right? This is just for this case, right? So, like, this is pretty simple, right? So, how do you show two sets are equal? You let an element be in one, show like set inclusion, right? Like one way and then the other way. So first off, since Q is in GH, Q equals like GH1 for some H1 and H, right? H1. Yeah. So let's let X be in GH. So we're going to show like one way. So let X be in GH, then X is GH2 for some H2 and H. Yeah. So, yeah. Okay, so now what? Well, I can rewrite X, right? So X is GH2, H2, sorry, GH1, H1 inverse H2. Yeah? Does everyone agree with this? Because H1 inverse is just identity. So, like, these two elements here are the same. Everyone agree with that. But this is just Q H1 inverse H2. Yeah? Everyone follow? So this is Q times something in H, right? Because, I mean, I don't care what this is. H is a subgroup, right? It's closed under, if H1 is in H, H1 inverse is in H. And then if I multiply two elements, not multiply, but group operation, two elements in H, it remains in H, right? So this thing is in H. So this thing is in QH. Yeah? So what did I do? I let X be an element in GH and showed it's an element in QH. So I have this, yeah? So now we show the other way. Now this one's easy because if X is in QH, X is QH1 for some H1 in H, then what is Q? Q is GH1. Let's use H3. So X is GH1. Q is GH1, right, from here. So GH1 and then H3. And then again, H1, H3, that's some element in H. So this is in GH. So I have QH is a subset of GH. So if I have two sets that are subsets of each other, then the sets must be equal, right? So okay, is everyone clear on this? Yes or no? I mean, you don't need to know the proof, but just think of this, right? It's basically saying if there's no difference, like 1 plus H should be no different from 8 plus H. It should be no different from 15 plus H. Should be no different from 22 plus H. So on and so forth, right? Because again, if you think of elements here, the class of 1 is just the class of 8, which is the class of 15, which is the class of 22, so on and so forth, right? Everyone clear so far? Okay. Good, you all follow. So, so now we could, this is the set of cosets. So now we could define a group operation. Define operation. So, okay, not define group operation. So we want to make it a group. So we need to define some binary operation. Well, define it as this. Yeah. So given two cosets, if I group the operation sends AH and BH to A star BH, where this is the operation in G, right? This is like, if you like, it's star 1. Yeah. But, I don't want to keep writing star 1 and star. So again, if you like, G under star. So, right, so like an example before, right? Example with G equals Z, H is 7Z, right? We say like, let's take A to be 2, B to be 3. Then we are basically saying 2H. Think of this as 2 plus H in this case, right? Star 3H, which is 3 plus H, because the operation is plus in this case. Is 2 star 3H, yeah? But 2 star 3 is 5, right? Because the operation is plus. So this is 5 plus H, right? I just don't want to write a lot of plus signs. So so I mean it makes sense, right? In Z mod 7Z, when you take the class of 2 plus the class of 3, you get the class of 5, right? Yeah. So, but the problem is when you check this is closed, there's an issue, right? Because take AHBH, right? Then, so we need to check it's closed. Well, let's take X in AH and Y in BH, yeah? So X is like AH1 and like Y is like BH2, yeah? Then AH1 star BH2, if you like star everywhere, this has to be ABH3, right? Maybe I'll skip the stars because it looks ugly. AH1 times BH2 has to be ABH3, right? If we are going to define it this way, right? If this is going to be equal to A star BH, then, you know, if I take an element in AH and take an element in BH and do the operation, I have to get something in here, right? Is everyone clear on this? Like, this has to happen. Agree? Or else, like, this thing is not well defined, right? And you see there's an issue here, right? I mean, this might not be possible. It's possible if we could sort of swap, you know, swap these terms, right? If I could swap the B and the H1 in a way, you know, move the B to the other side, right? Things would be fine, right? Because like, I mean, even if it's instead of H1 I have another element in H, H1 times H2 is still an H, right? So the issue is you can't really swap, right? I want to be able to say something like this. HB is BH for all B and G. All right. If I have this thing, I'm done. Instead of B, let's use G, right? So before I continue, does everyone understand what this means? When I write HG is GH. It doesn't mean this, okay? It does not mean this. Yeah? Do not do this, okay? So if you do that, because this is just abelian, right? This is the statement for abelian. Yeah, that's a good question. Good, you're paying attention. So this is just abelian, right? So I mean, normality is a bit different, right? Because this is H is just any element in H, right? So what this means is like H1G is GH2, right? So we're basically saying like we could swap, but it might the H term might be different. Yeah. Does everyone understand the difference? So this is a lot stronger. Okay, abelian is like just a lot stronger. That's why we write capital H. When we write capital H, it means we could take any element in H. So now do you agree if we could swap, right? So if AH1 BH2, if I can swap at the expense of changing the H, I'm done because this is ABH3 H2, right? Or if you like H1 prime, let's use H1 prime. Um, well, it doesn't matter what element this is because this is just some element in H, right? So this is an ABH, and therefore it's well defined. So this is what we call normality. Normality, right? So we say a subgroup H is normal. H is normal if this is true. Does everyone understand why we need normality to get like closure? Right? Again, to be a group, this has to be binary operation, right? So you must be closed. You must take something to your respective, to whatever it, you must take these two to this thing. If right now, if I just write this element here, it doesn't really lie in here. Yeah. uh, Everyone follow. Okay. So inverse is easy. Yeah. So inverse, what's the inverse, everyone? Like, um, basically inverse. Whoa. So inverse, right? AH star what is identity. So before that, right? What's the identity? Before I even ask that, what is the identity in this case? Anyone? So if I have AH, what do I need to multiply to get AH back? If you think about it, it's gonna be EH, yeah? Because how do we define this? I just wrote it in the last page, right? It's A star EH. But A star E is just A. Yeah. I mean, it makes sense, right? The thing you quotient out by, this thing should be 0. Yeah. Like in Z mod 7Z, any multiple of 7, anything in H, anything in 7Z is identity, right? It's the class of 0, right? 7, 14, same thing here. EH, right? If this is G and this is H, H is like your identity. Any multiple of 7 is 0, right? So, and the inverse is, hopefully by now you see it's this, right? Because of this option. Everyone clear on this? Makes sense? This should be review for all of you. So I hope it makes sense. So um so one more thing, right? Ren is AH equal to BH, right? So this is exactly what you think, right? Just multiply by, you can multiply by A inverse on by A inverse H on both sides. From here, we know what we get. On the left side, we get H, right? On the other side, I have A inverse H, BH. And this is, by definition, it's this, right? I just didn't write all the stars because, I mean, it'll look really ugly. But this, so it's when this is true, right? Now, what does that mean? So if we go back to proposition 1, if I have AH is equal to EH, this is if and only if, but I only prove one way, but this is if and only if A is in H, right? So same thing here. A inverse BH is equal to EH or H. That's if and only if A inverse B is in H. Yeah. For example, like, for example, the class of 2 in here, right? I know that the class of 2 is not the class of 3 because like 2 plus H is not equal to 3 plus H. Because if it was, then I just apply this, right? Then 2 inverse plus H. So if this is true, if 2 plus H is 3 plus H, then 2 inverse plus 3 is in H, right? But 2 inverse is negative 2, right? Plus 3. So that means 1 is in H. But H is 7Z. So, right? Like, this is just not true, right? 1 is not in 7Z. 7Z is like multiples of 7. So 0, 7, 14, um, so on and so forth. I mean, I'm just saying class of 2 not equal to class of 3. Okay. Okay, hopefully you all follow. So if H is normal, G mod H is a group. Yeah. So do be careful. G mod H still is a set if H not normal, right? I mean, it's still a set. You can still define it, right? If H not normal. It's just that you don't have an operation, a well-defined operation on it. Okay, let's go on there. So which groups are normal? Well, abelian groups are normal, right? By I mean um have all, before I go back, have all normal subgroups, right? Go back. Here. Okay. Right. I mean, this is clear, right? Because if I have a group, a subgroup, I don't care what it is. I know something stronger, right? I know this is true. So it's pretty clear if it's true on element, it's going to be true here, right? So abelian is just way, 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 way stronger. So in the case of Z, right? I didn't really need to check that subgroups were normal, because here Z is abelian. So all subgroups are normal. Yeah. It's because A plus B is B plus A. Right. So I didn't really need to check anything, right? So let me just give an example of like a non-normal sub. So obviously, for a chance to find non-normal subgroups, you need like non-abelian groups, right? And hopefully the first thing that comes up to you, what's the first group you learn that's like non-abelian? It's like, I mean, aside from matrices, it's like SN, right? The symmetric group on like n elements. So in this case, it's 3 elements, right? So I'm gonna trust you all know how to cycle compose. So the different cosets are here, here, and here. So again, once I get the whole group, I'm done. So now I'm gonna let H be the group 1, 2, and identity. Yeah. So EH is again 1, 2, and identity. This thing just multiply, right? So what's 1, 3 times 1, 2? Well, where does 1 go? 1 goes to 2. 2 goes nowhere here. So now what? 2 goes to 1, and then 1 goes to 3. So 2 goes to 3, and then 3 goes back to 1, right? So it's this element. 1, 2, 3, 1, 3. And you can check that this is, the remaining 2, right? Okay, everyone clear on this so far? So again, from part 2, like, why do I not, I'm basically saying this is redundant, right? Redundant. Like, you could write out all 6, but I'm saying some are equal, right? Because I'm using this. So if I go back to I'm using number 2, right? If I take an element Q in GH, then QH is GH, right? So if I take an element in here and I consider a different representative, it's going to give me the same thing. So here, this is just the same as 1, 3H, right? If I took a different element instead of 2, 3, if I took like 1, 3, 2, then like 1, 3, 2H is the same as 2, 3H. You can check this, just multiply. I mean, not multiply, but cycle multiply, right? So yeah, so some are like redundant. Okay, so from here, like, right, this is not abelian. So let's check EH times 1, 3H. If this is true, right, if this is well defined, then this should just be 1, 3H, right? Because this is 1, 3 E circle 1, 3 H, right? Again, we defined the operation to be like this, right? But E with whatever identity is just 1, 3 H. But this is not true, because there's an element here. Let's take an element. This is 1, 2. There's an element 1, 2 in here. There's an element 1, 2, 3 in here. And if you multiply 1, 2, and 1, 2, 3, what you're going to see is you're going to get 1 goes to itself, because 1 goes to 2, 2 goes to 1. So you're going to get that this is the element 2, 3. So this is 2, 3. But there's no 2, 3. No 2, 3 in here. Yeah? So you see H is not normal. Yeah. I mean, here, I showed it because group operation just doesn't, is not a binary operation. So let me just end with one thing. So we want to generalize normal subgroups to rings. And it turns out the right thing to consider is something called ideals, which go over next time. Yeah. So we sort of want to consider cosets, right? But instead of a group, we have a ring. So instead of G, like capital G, I have like capital R, right? So now the question is, what does cosets mean, right? So like what are normal subgroups? And it turns out it's something called ideals. So okay, everyone clear on where we're going? And at least where your professor will be going Friday and Monday. So yeah. Okay, cool. I will see you all next week. All right, no problem.